So today we're going to talk a little bit about maybe a little more formalism with regards to feedback systems. Can you all think of maybe some feedback systems that you already know about that are biological that you maybe have already talked about with Dr. Brock that are important?
Thermoregulation.
What?
Thermoregulation of the body.
Right. Okay. Any other examples? Okay. Glucose control, right? Blood pressure. So most all of our biological systems, have some inherent aspect of feedback control because feedback has a bunch of advantages in terms of stability. And so, we've actually evolved some really neat feedback systems to be able to create that stability, which are important for homeostasis. Last time, I think at the end of the last class period, we were talking about the cerebellum. And cerebellum is a great big kind of a sub-program that the motor system uses to regulate fine motor movement, and it has some very, very beautiful kind of feedback systems where we take proprioceptive information and compare it with instructions from the brain, get an error signal, compute a trajectory, and then execute a motor movement. And so we'll actually go back to the cerebellum, during today's lecture and put a little more mathematical rigor to what these feedback systems are capable of doing. So a lot of feedback systems. So the basic diagram for a negative feedback system is shown on this slide. And the important thing, the takeaway, the thing that you have to memorize for this class is the closed loop equation that describes the behavior of the system when you have negative feedback. In other words, when you have some kind of a H that feeds back. If you don't have H, basically E out is just K times E in, or the feed forward part of the loop. But when you have that, you basically are comparing this to this and calculate an error signal, which then drives the plant. So the plant is the K is the big system. This is like the motor system or like the cerebellum. And so the feedback loop is kind of like the proprioceptive system. It's what's sensing, what's going on. Now, one of the immediate kind of observations when you look at this closed loop equation, and more generally, we have basically, so this doesn't really have a lot of frequency information, but in a more general sense, this has frequency information, and then this has another term to it. And so it really kind of, the more kind of general term is GC equals K G of S divided by 1 plus K H of S G of S. And that's kind of the more general, which has the kind of the frequency information in it too. But the general kind of, I guess, observation is that for K, if you make K large enough, if the feed forward loop has enough gain, what happens is that the closed loop function just becomes 1 over H, or 1 over the feedback part of the loop, which is kind of not necessarily intuitive, but it's kind of important because what you can do with these feedback systems is you can design the system such that you get a lot of gain in the feed forward system, and you can get rid of all the frequency dependent information content by just making the feedback loop be frequency independent. So basically, your closed loop gain just becomes a function of the feedback loop and not the feed forward loop. So there are 3 advantages that why we use negative feedback. The first thing is that feedback stabilizes the overall system gain, and so the kind of the equation that describes this is the change in closed loop gain divided by closed loop gain is 1 over KH times the change in open loop gain divided by the absolute value of the open loop gain. Okay, that equation may not mean a whole lot, but let me put it into some context. And actually, this is how you derive that. I just went ahead and derived that for you. So again, the change in closed loop gain divided by closed loop gain, or the percent change in closed loop gain, is 1 over kh times the percent change in open loop gain. And so again, to put this back into context, a good example might be is how large must the feed-forward gain be to ensure that a 100% change in feed-forward gain results in only a 0.1% change in the closed-loop gain. And so what we have here is the 1%. That's the delta D GC over GC closed-loop gain is equal to that 1 over KH. And here we've specified H to be 1 over 10. And so this is a 100% change, and this is the dk over k. And so you do the mathematics, and it turns out that any value of k over 10 to the fourth will ensure that a 100% change in feed-forward gain results in only a 0.1% change in closed-loop gain. And so basically what you're doing is you're sacrificing gain, because obviously your gain now is going to be 1 over h, or 10. And so basically we've gone from a gain of whatever to a gain of just 10, but because of that we have allowed the system to have much more gain stability. And so basically that makes the system less possible to have some singularities. So basically we've sacrificed gain to get gain stability. So that's the number one. That's the first thing. The second thing that negative feedback produces is that if we introduce distortion, which is present in any system, that if we add distortion, which is D, which is added to, and don't let me confuse you, this is still a negative feedback system because I have a negative K in that diagram. So in this diagram, I'm adding amount of distortion to the feed-forward gain, and it turns out that when I look at my kind of equation that describes the system performance, I actually, by having the feedback system, in other words, having that H in the diagram there, I decrease distortion, which if I didn't have H would just be added as a D, right? Okay, it's just added to D if I took that H out. But with the feedback loop in there, I actually decrease the distortion by 1 over KH. Okay, this is a trick that made billions and billions of dollars for those who first recognized this particular principle, because when integrated circuits became very inexpensive, it was very possible to get very large gains. And so where one used to spend many hundreds of dollars on a linear amplifier, just say an audio amplifier for your home stereo, it became possible just to use these very cheap high gain integrated circuit chips and put a negative feedback loop in them and decrease the distortion lower than anything you could get with really good electronics. And so it allowed one to again sacrifice some gain to decrease, in this case if you're looking at an audio system, harmonic distortion. And so that made consumer electronics become much cheaper, just that one equation that I'm showing you there. And that's true for all linear amplifiers. And this is the way that is derived. I derived that for you. And so the third advantage is that feedback improves frequency response. And so a lot of times, we need an amplifier, a system that has a response that goes out to many megahertz. In our biological systems, we're really looking at maybe 10 kilohertz as kind of being an upper limit. But because we are able to make so much feed-forward gain, if we make the big system, the one that actually is doing the work, we make K large enough, we can make the closed loop gain be 1 over H, and we can design 1 over h to basically just be a resistor divider, and so 1 over h of S becomes just a constant. It just becomes 1 over h, which, you know, is basically frequency independent. And it's not exactly, but, you know, that's kind of the idea. Okay, so those are the three big advantages of negative feedback systems. That's why as biomedical engineers you use these negative feedback systems, and why our brain has evolved to do the same thing. So to look at this frequency dependence, I ran through a little example here, and I'll run through another one. But if I take this out, my gain function, okay, is just equal to 10 to the 7th divided by S plus 10 to the 3. In other words, I have a single pole that has a break frequency of a meganaught equals 10 to the 3, and it has a gain, the low frequency gain, G, low frequency, is just equal to, so basically you don't have that, it's just 10 to the 7th over 10 to the 3, it's equal to 10 to the 4th. Okay, so I drew this here, so this is what the gain function, if I just have that open loop function, looks like this. So a single pole will decrease at minus 20 dB per decade. Okay, and so that's without the feedback loop. High gain, but really doesn't have a really high frequency response. Okay, so let's put this back in again here. Okay, and when I put a little feedback loop here, I mean this might, so this guy right here could easily look like a little resistor divider. So basically I have, you know, a 10 to the minus 2 would be a 99, say 99 kilo ohm, 1 kilo ohm. Okay, and then here's my output. So basically the H is now just going to be 1 over 1 plus 99, or 1 over 100, so it's 10 to the minus 2. And if I put this little resistor divider in that feedback loop, my closed loop gain looks something like this. Okay, and so I calculated that for you. And so in this case, my break point here, my meganaught is going to be equal to 10 to the 5th, and my gain is going to be, when this is very low, when that's close to 0, it's going to be 10 to the 7th over 10 to the 5th, which is equal to 10 to the 2. And so I now have decreased the gain here, but I've extended the frequency response out to 10 to the 5th. And so this illustrates this principle of what's called the gain bandwidth product, which is constant. So if I multiply the gain times the bandwidth, it should be the same. And in fact, if I do it for those two cases that I just showed you, the first case is a gain of 10 to the 4th and a breakpoint of 10 to the 3, and that gives you 10 to the 7th. Second is a breakpoint of 10 to the 3, I'm sorry, 10 to the 5th, and a gain of 10 to the 2nd, which gives you also 10 to the 7th. I'm sorry, 10 to the 2nd and 10 to the 5th, which gives you 10 to the 7th. So again, that kind of illustrates this principle of what's called the gain bandwidth product. You sacrifice gain in order to get higher bandwidth. Any questions about that? Okay, so how do we use that as biomedical engineers? We use that a lot with our integrated circuits. So here's an example of a non-inverting amplifier. I have a OP7 or a 741C op amp, and so it's a linear op amp. And if I put a little resistor network here, some of the principles are that this voltage should be 0, and if I look at the kind of the feedback loop there, it turns out that that's just H looks like this. You can kind of make the analogy that I have a very high feed forward. You know, K in this case might be 10 to the 7th plus some frequency information. And then H, if I have a little resistor network here, my gain in that resistor network is just the RF divided by RF plus RI. So basically I get an E out over EI or H function that looks like this. And if I put that back into my other equation, my closed loop gain is K G of S divided by 1 plus K of S G of S. If I put that back in, that gives me my familiar equation to, I'm sure, most of you, which shows that the non-inverting input to an op-amp amplifier, linear amplifier, is equal to the feedback resistance divided by the input resistance plus 1. Okay, so I can use my feedback theory to, describe, what happens to my little linear op-amp. Okay, and so this is a typical characteristic curve for the 741 class linear op-amps. And if you look here, you can see that my my low frequency breakpoint is really pretty low. I mean, it's maybe pretty hard for y'all to see this, but this is 10 to the 10 to the 5th. So basically I've got 100 dB gain. So on my scale here, I'd have to go way up here to 100, and it goes down something like this, and my breakpoint's at looks like about 8 hertz. So it's going to be 6 times 8. So basically I've got like 68 for my cutoff point radians. Okay, and so that's kind of what this curve kind of looks like. Now, call that better here. So this is like 115 dB, and then this is 2 pi times F, and it looks to me like F is like 8. So 6 times 8, about 4850. If I make this scale be a mega. Now in general, we can play around with these. So again, the closed loop gain is just the impedance here divided by the input resistance. So if I make my feedback resistor here be combination of so I'm going to make RF be a resistor and a capacitor. So I have RF and a C. Okay. Then my ZI, this part right here, the Z feedback, because I'm going to actually put that right there. If I redraw my diagram now to where it looks more like RI. I'm going to have a resistor and a capacitor like this. Okay, if I do that, turns out that now this impedance is basically the product of this over the sum, so it's RF times 1 over SC divided by RF plus 1 over SC, and so now my Z feedback is going to be equal to, I multiply that by SC, it's RF divided by 1 plus S RF times C. And so for this particular case, if I have some kind of an input resistance RI, if I have this be RI, my gain is just RF over RI divided by 1 plus S RF over C. And so you see you got one pole, and by doing this I increase the frequency response of my linear op-amp. Any questions? So feedback has this huge advantage of being able to increase bandwidth at the expense of decreasing gain. And so in this particular case, where I just drew this would be a gain of, let's just say we chose RI. Let's say it's, when we say RI equals, say, 10, now let's say it's 1K. And then RF equals 100K. Okay, that gives us a low frequency gain of 100 or 20 dB. Okay, and my low frequency cutoff now is going to be 1 over RFC. So this number here, where it cuts to 0, where it starts starts cutting down, excuse me, it's going to be this number right there. Yep.
Why do we want to increase the bandwidth?
So it turns out that in order to not alias, I don't know if y'all talked about aliasing. Y'all talked about that?
If you sample too far apart, then you don't get the proper signal.
Right. And so if you have a signal that has frequency components, let's suppose that we know a priori that we're looking at a signal, say from our brain, that has frequency components that are significant. We do a power spectral density function, and we know that it has a certain amount of energy that's up at, say, 1 kilohertz. Okay? If we use the amplifier in that first case, okay, we would not faithfully reproduce that. We would only amplify the part of the information, see, that's lower frequency than what it is that we are really interested in. And so one of the principles in biomedical instrumentation is that you have to know what the frequency characteristics are of the signal that you're trying to amplify or reproduce in order to reproduce it faithfully. And so a lot of times we measure very, very small signals. I mean, this could be a very, very small signal from an optical sensor, say, and we are looking at maybe a coherence function. That's what we do in the lab. We look at very, very high frequency coherence functions. Actually, the frequencies that a lot of times are appropriate for some of the instrumentation that we use are up 400 or 500 megahertz. Now that's a little higher than most of our biological signals, but it turns out then that having this bandwidth to be able to reproduce it becomes very important. And so what I can do is I can cascade these blocks. They're very inexpensive. And so I can sacrifice the gain. But see, if I have the bandwidth out to where I get the whole signal, okay, I can just add another cascade and another one and another one, and the overall gain function is just the product of the individual gains. And so, I mean, again, it's just a trick that we use as biomedical engineers to, get all the signal. And if we don't, let me tell you, if we don't do that, what happens is our measurement becomes corrupted. And so we have to, so again, back up for a second. In order, most of the things that we do, we end up digitizing them to be able to save them, to be able to store them. And so we know that we have to digitize at least twice the highest frequency that's in our signal. So we have to pass the signal along with our amplifier, okay? And then when we do our sampling, we have to sample at twice the frequency of the highest component that's in our signal in order to not alias. Otherwise, the information that we recorded in our data analysis is going to be totally corrupt. And there are many, many experiments that we do. Actually, we go back and we look at it, and we figure out, after we've done the experiment, that perhaps we have not, had the appropriate frequency response, or maybe we haven't sampled at high enough frequency, and then we have to go back and we have to start all over. We have to do the whole experiment all over again. And so, paying attention to bandwidth, and if you're, sampling, you have to sample at whatever twice the highest bandwidth is. Then, if you don't do that, well, your data is corrupted. Any other questions? Okay. Now there's a flip side to this too, and that is that a lot of times, like at the end of last class, We talked a little bit about the measurements that we could do on a person who's trying to get their driver's license to measure coordination. You know, I just drew something up on the board, I think. But we can actually be very precise mathematically at looking at a person's motor response. And having done this, I will, kind of draw out for you kind of what a typical, kind of a typical curve might look like for somebody that's doing just a tracking test. So remember, the cerebellum is how you track. It's this, finger to nose, tracking. And so we talked about just making a video game. And so if I make a video game, and so this is my input, and I tell you that as the input comes in that you have to trace it, reproduce it, and do it as fast as you can. Well, as it gets faster and faster, what happens is my response gets out of phase and it gets lower and lower amplitude. Okay? Now, I mean, you can see that if you try moving something that's moving really, really fast, you can't keep up with it, right? Right? And so your amplitude response to a given stimulus, tracking stimulus, where you have to move your hand or your joystick or whatever, you lose phase, and then as you lose phase, well then your amplitude drops off. So basically you can stay phase locked up to about 10 hertz. And so when I do this experiment on normal subjects, where I have them play a video game of some sort where they have to track a moving ball, okay, your response looks something like this. You can track it perfectly up to about 2 or 3 hertz. Remember, this is a mega, so that's 2 pi times the frequency. So at a break point of roughly 10, you begin to lose performance, and that performance drops off very quickly. As a matter of fact, when we do the experiment, this drops off at about minus 40 dB per decade. Okay. Does anybody want to take a stab at what the closed loop equation is for this? What can cause your response to drop off at 40 dB per decade? What?
Square pole.
Pole squared, right? Okay, so this is going to look like S plus omega naught squared. Okay, and so if we know that this is 10, okay, we know that then this is going to be 100 right? So basically, I can go into the lab and I can, test your performance, and then I can write an equation that describes how well you perform that task. Isn't that cool? And so if you have somebody that has a cerebellar problem, okay, this curve might well look something like this. So in this case, and so I can look at that break point and I can set some norms. I can set certain numbers that say, well, this is normal and this is abnormal. And so from a quantitative standpoint, I can say, maybe you shouldn't get a driver's license, or maybe you should. Okay? So these tools that you're learning, and I think y'all learned this in Dr. Milner's class, is that right? Is that where y'all study this? Systems? I don't know. Maybe?
We were going to. That's where we're headed.
You're going to?
We did it in circuits as well.
A little bit in circuits? Okay. But in general, I should be able to give you, any kind of a Bode plot, and you should be able to write the transfer function. Right? Y'all know how to do that, right? It's a powerful tool. Here's another example. And so many times we want to have a band pass. We want to have a certain amount of amplitude that we amplify between a low and an upper cutoff frequency. And so I can add a high pass along with that low pass filter, and so basically I have a high pass filter here, and this is the low pass filter that we just talked about. Okay, and again, if you put in, go back to that equation that gain, in this particular case, this is an inverting amplifier, so it's going to be negative the feedback impedance divided by the input impedance. Well, the input impedance now is R1 plus 1 over SC1. The feedback impedance is going to be the parallel combination of C2 and R2. So it's R2 times 1 over SC2 divided by R2 plus 1 over SC2. Anyway, if you just do the mathematics, it turns out that you end up with a equation that actually has, for low frequency, a gain which increases it. For very, very low frequency, you get basically a gain that increases at 20 dB per decade, and then you get, when this S cancels with this one, you get basically a flat curve, and then when you get up to the very, very high frequency, you start to see this break point. So it's basically two poles and a zero, and the curve for this amplifier, if you do that, looks something like this. And I just went through and I put some numbers in just to kind of show you how you can design. This is a bandpass amplifier that has negative feedback, and so it's stable, okay, has low distortion, has a gain of, in this case, 20 dB, so it's got a gain of 100. And so that's how we design. It's how we design our amplifiers. Okay. And so again, the reason that I do this is because I a priori know something about the noise and the bandpass or the signal content. I basically have to do some sort of a study to find out that I have to bandpass something, and I know what the low cutoff is, the high cutoff, and I design my amplifier to match that. Why do I not want it to go all the way to zero? My amplifier.
You
Yeah.
lose resolution as you drop off closer to zero.
No, you don't lose resolution. All of these amplifiers have noise. And one of the characteristics of all op amps, all of linear amplifiers, is what's called 1 over F noise. Y'all study that? And so if you look at an amplifier without being bandpassed, if you don't do this, if you look at the just the noise. So basically you take the amplifier, you short the two inputs together, and you just look at the noise in the circuit. It looks like something like this if you get enough gain. And so that's not part of your signal. So you want to get rid of that 1 over F noise. So basically you set your lower breakpoint above that 1 over F. A lot of times, I don't know, do y'all do a lab where you measure the electrocardiogram maybe? Okay, what's the problem if you DC couple the electrocardiogram?
Doesn't it saturate?
Yeah, your electrodes are usually silver chloride. They're batteries. So you have all these little batteries, and you wiggle around a little bit, and you get what's called baseline drift. So your EKG, instead of looking, like this, your EKG is doing like this, and it's drifting all over the place, and it'll rail out, and then you'll begin to see it again over here. Y'all know what I'm talking about? Y'all have experienced that? Okay, so that's why you don't want to DC couple a signal. So basically you have to know that the EKG is between about 0.1 hertz and about 200 hertz. So you design your amplifier just to do that. Right? Okay, these are powerful tools. This feedback stuff is really, really important. And biomedical engineers say y'all can put quantitative numbers on these feedback systems where your colleagues over in liberal arts, they don't have a clue as to what this is. Any questions? Okay, another concept that's really important are proportional integral derivative controllers, which kind of fits into this topic of feedback control. So if you work as a biomedical engineer, I can pretty much guarantee you somewhere in your career you're going to have to deal with this, okay, because that's something that's very, very important. And so there are a lot of companies, Analog Devices makes them, TI makes them, Silicon Labs makes them. And so if I want to buy a PID controller, I go to my Newark catalog or go online and try to pick something that kind of matches what it is that I want to do with my controller. Now the idea of a controller, just to kind of back up for a second, the controller is something that, for example, is going to measure measure some parameter. Let's say it's temperature, because I'm going to show you an example in a minute. Temperature. And so I've got a thermocouple and I'm measuring temperature. So that's my feedback part. And then over here I have a set point. I want to keep whatever it is that I'm trying to control at exactly 37 degrees. Okay, and then I have this feed forward thing, which is some kind of a heater, and maybe I'm heating your blood, maybe I'm heating your skin. I'm going to heat something, but I have this loop and I want to keep your input at 37, see, while measuring your actual temperature over here. So that's what a PID controller does. So I have to have some way to measure something. That's where the 12-bit A to D converter comes in. And so I have an input. See, I have a diagram here. This is what it looks like. So I have an input, which is my set point. This would be like 37 degrees. I want it to be 37 degrees. This is actually the temperature that I'm measuring. Okay, and this is my thermocouple. It's giving me information back. And my controller consists of this summing point here and a proportional, integral, and a derivative part of analyzing the error signal, which is the difference between my H. This is my 1 over H signal here that's coming in here, is subtracted from my set point to get my error signal, and the error signal then drives whatever I do to my heater to adjust this temperature to try to make it be 37 degrees. I mean, it could be glucose. It could be a glucose controller. Maybe I want your blood glucose to be 100, and I'm measuring your glucose continuously, and so I'm going to be delivering. Now my plant is a way to deliver insulin to maintain your blood sugar at exactly 100. That's what your pancreas does. All right. So proportional, integral, and derivative. So what I'm doing is I'm taking that error signal and I'm taking the proportional, just multiplying it times a constant. The integral, I'm integrating the error, and the derivative, I'm taking the first derivative of the error with respect to time. Why do you think I want to do that? It's just a contrived exercise, or does it have some advantage? Yeah.
It will tell you the sensitivity of how much
yeah,
you need to change?
Absolutely. So I can adjust, how fast it responds. I can adjust the overshoot. I can adjust the steady state error. And there's some things where, one thing you don't care about, but maybe something else you care a lot about, right? I mean, if I don't care about, the transient response, maybe my temperature controller warms my blood up to where my blood gets to be about 50 degrees centigrade. Then what happens? Then you die. That's right. That wouldn't be good. So my controller, based upon what you're doing, you're going to set how fast it responds, how much overshoot it has, and basically whether you have steady state error. Okay, so proportional gain, integral gain, and derivative gain. And this is a good diagram. And the important things here is that the Kp, the proportional constant, decreases the rise time. Ki eliminates steady state error, and Kd decreases the overshoot. Those are actually the more important parts of that diagram. Those are the important ones to remember for this class. Okay, so let me give you an example of how we use this. So here's an example where we have our controller and some kind of a plant function, and so I have some kind of an input E, which is my error signal, and I have an output U. Okay, so E is the input, U is the output, and I have the proportional gain times the error. My integral gain, I integrate E with respect to time, and my derivative, I take the first derivative of the error with respect to time. Okay, and I can write that in the frequency domain as a function of j omega, which is kind of shown in that last equation. Okay, so I have the Kd times j omega squared, my Kp times j omega, and my Ki, just the Ki over S. Okay, here's an example. So I'm going to show you, this is a mechanical example. So y'all took physics, right? Y'all have had physics. Okay, here's a little wagon, and the wagon sits on a frictionless rail, and it's connected to a spring. This is a spring and a dash pod. Okay, so we know that the spring, if I pull this here, the force that I get from the spring is going to be minus Kx. The dash pot is going to create a force which is some constant times the velocity, so it's going to be the first derivative of x. And then the little cart has mass to it, so it has, to accelerate it, it's mass times acceleration. And so the amount of force here that I have going one direction has got to, some of the forces have to be equal to 0, right? And so this is the force that pulls this direction, and the three forces that pull this direction are mass times acceleration. The dash pod is velocity times b, and the spring is kx. So that's my equation that describes the movement of my little cart on the frictionless rail. Okay, so I can now say, okay, well, I'm going to pull this with a step function. I'm going to make f of s be 1 over s. Okay, so now I can basically solve that equation for x. That's x of s of a frequency here. And it turns out that my ruling equation for the system that I have here is the step function forcing 1 over s squared plus 9s plus 20. And that describes the motion of my little cart as a function of time. And so my x is the displacement from its initial position. Okay, it turns out that because I got to make the problem up, turns out that this actually has an exact solution. Now most things in nature don't. Okay, so yeah, understand that this is kind of contrived, but anyway, you can factor this out, and so you basically have, if you do partial fractions, you get 1 over s times 1 over s plus 4 times s plus 5, and this actually has an exact solution. If you take the Laplace transform, you take the inverse Laplace transform, it turns out that it's 1 over 20, so it has a steady state error plus an exponential over 4 minus 4 and an exponential over 5. And if you plot this out, which is much easier to do with MATLAB, there's the MATLAB code, turns out that x is a function of time. So I've plotted here the output from the MATLAB program. This is x and this is time. Okay, but that's what it looks like. That's how the cart moves as a function of time, given whatever the parameters were for b and k. Any questions? That's kind of from physics. That has nothing to do with control systems. Okay, that's just kind of to lead into what I'm trying to get to. And you notice that this has a steady state error of 0.05. That's this part right here in my solution. That's called steady state error. I mean, if you want to call it that. So basically, it never gets to 0. Okay, now let's do the same problem, except now I'm changing it. I'm changing the problem. Okay, so don't get confused. I've changed the problem, and so now the problem is I want my mechanical system to follow a step function perfectly. So I'm gonna force it with the step function. So this is my input. It's gonna look like this, and I want my output to look exactly like that. I want my output to be as close to that as possible. I want it to look as close to that as I can possibly get. So I've changed the problem, and I'm going to do it with the feedback loop, because I know, and you all know now, that this is the right way to do it. You do it with a feedback loop, because then I can force it with a function and come up with some solutions that will make it move exactly how I want it to move. It may not be, this is position, it may be temperature, it may be glucose, it may be blood pressure, it may be something else, but I can do it with any kind of, whatever you tell me it is, I can make a PID controller that'll control it. Okay, this is just a simple example. So here I've put in a negative feedback loop. My negative feedback loop, H is equal to 1, right? So remember, closed loop gain is equal to Kg of S divided by 1 plus KGH all of S. And so in this particular case, it's KPK, that's feed forward gain, divided by 1 plus KPK times 1, because H is 1, and that's my closed loop function. Okay, so now I've got desired position, and the controller is going to help me do that. So I've put now my PID controller here, and I have this proportional gain function K that I can adjust to make it work how I want it to work. So there's my mechanical, that equation up at the top here describes the mechanical system. That's the feed forward system. So that's the mechanical system transfer function. And I plug that now back into my equation, you know, the 1 over KH, or K divided by 1 plus KH. And I get my solution. So this is my closed loop system now. That equation then describes that system with a feedback of 1. So this system, I now have my closed loop system now is 1 over j omega squared plus 9 j omega plus 20 plus Kp. What is Kp? My controller.
Proportional control.
That's the constant for how much proportional control I give it. Okay. I can make that number be anything from 0 to infinity. Now, I can't get an exact solution. This has no exact solution. But I can, you know, get a solution very easily by just modeling it with MATLAB. And this is what the solution is if I say Kp equals 300. And I would encourage you just to play around, you know, with your spare time. You'll have a lot of spare time. So just play around with Kp and just see how that affects, you know, the gain of the controller. Now I want to point out to you that my desired, so I have the problem here is I want it to follow an exact step. So my desired solution, my desired response would be what I just drew in the red line. You notice that there is a constant steady state error. So it never does actually get to where I wanted it. And so for many problems, you know, this could be a real issue. You also notice that it has an overshoot of 20 or 30%. And so if I'm really sensitive to, say, temperature, or, you know, I can't tolerate a blood pressure over a certain amount, this would not be a good solution to the problem. Okay, so it's better than if I had no feedback. Remember the response to no feedback just looked like was an exponential, remember? So this is maybe a little better, but still not real good. Okay, so let's go on ahead and add our proportional. We already had that. Now let's add the integral and the derivative of the error signal to our feedback loop here. Okay, I still have the same mechanical system. Okay, and so now when I get my solution now to the closed loop gain function, my closed loop gain function now is this equation right here. Okay, and again, there's no exact solution. I can express it different ways. And if I put it into this form where I've got my j omega cubed, my j omega squared, my j omega, and my k, and so I have ki j omega squared plus kp j omega plus ki in the numerator, and then likewise down in the denominator. So now I can write this into my MATLAB code. And so here's an example where I chose proportional gain to be 350, integral gain to be 300, and my derivative gain to be, say, 50. And I would argue that this actually is a pretty decent response. So again, here is my, it was absolutely perfect. You know, it would look like something like that. But here, there's no steady state error because we have integral gain, and there's not a lot of overshoot. So I would kind of proposition to you that this is a pretty good solution to that problem. Okay, so that's how you use a proportional integral derivative controller. What do you think? Andre, have I convinced you? Maybe. Okay, so now I want to go actually through a real example. Okay, so let me. This is just truly. This is just for fun. I mean, there are very few things in class that are just for fun. So this is actually not on quiz or anything else. I just want to tell you a little bit about a project that kind of illustrates some of the principles. So this is. I want to show you exactly how you actually in real life use this. Okay. And so there's a lot to this that's not relevant. Let's see if I can figure out. So back about it was actually in 2004, the Army came to us, to our group, and said we want to design a blood warmer. Okay. Now the problem is that troops in Afghanistan and Iraq were dying not because they were shot or injured or they got hit with an improvised explosive device, but they actually died because of hypothermia. And so one of the things that happens if you're injured, the Army is so good now with the medics that if you start losing blood, they actually have blood replacements that they can give you in the field. So you get injured, you lose blood, you basically very quickly in your unit you're going to have somebody that can give you a blood transfusion or a blood substitute. And the problem is, though, that you can't, if you're out on a mission, it's really hard to keep it warm. And so you have to have a way that you infuse back in something that's warm. If you give somebody that's already hypothermic because they've lost blood, if you give them a blood replacement that's cold, basically you just send them more and more into temperature shock. And so some of the numbers are that there's 90% mortality if your core temperature, that is basically your inside temperature, gets to 32 degrees centigrade. So it doesn't actually have to drop very far. You start off at 37, and the mortality gets really, really high as you get to about 32 degrees centigrade. So hypothermia, you've lost blood, you're probably acidotic, you may have some trouble clotting because a blood substitute doesn't have platelets as a general rule. And so basically we have to have some way to warm your blood. So it has to be rapid, portable, no special training, has to be idiot proof. These are all the design criteria that the Army gave us. And it turns out that it's very difficult to do this with a battery. So an electric heater doesn't work because you can't carry around, on your back, you can't carry around 3 or 4, batteries like you have in your car. It's just not a solution. So you can get a lot more energy in a chemical, kind of a combustion than you can, and it's a lot more portable. Okay. And we had some criteria. You can't go over, basically you can't go over about 42 degrees centigrade, and you have to have this thing that'll run for a couple hours. So this is our solution. So you're going to have some kind of a heat exchanger. So we had, we actually built a device where we had the blood come in and blood came out down this coil, this kind of a tube here. This is what it actually looked like when we manufactured it. So we have thermocouples at the input and thermocouples at the output. So we're measuring the temperature in and the temperature out. Turned out that we ended up only needing to use a little propane heater with a catalytic converter. And so you charge this thing, you can hold it in your hand. It has three nozzles that control high, medium, and low flow of the propane into the catalytic converter. And so we can control this with only 8 bits. So with 8 bits, you've got 8 states, 0 being no flow, it's turned off. Then there's 7 states where we can turn these valves on and off, just a binary code. So, this would be our 1, 0, this would be the 2, 0, and so on. And this actually was what it looked like when we actually manufactured it. And this is actually the controller. So as a part of it, inside this, there's this controller. So underneath this panel here is actually a little PID controller. The chip is right here. This is the chip. It's a Silicon Lab chip. Had a 10-bit analog to digital converter. Had enough memory where we actually had 4 different kinds of inputs that we could put in. We had a nice display that we could tell the operator that it was operational and what the temperature was, so they could monitor that and tell if there was a fault. And so these are some kind of descriptions of how the PID controller. So again, it's just like what we just described here. We have proportional, integral, and derivative control of an error signal, which is the difference between the input and output temperature. Turned out that actually, when we delivered it to the Army to be used in the field, there was actually no pump. Another group actually designed a little pronged needle set that in the field the medic could actually stick you in the groin, and it worked really cool. It would actually go into the femoral artery and vein. So we actually took the arterial blood, circulated it through our heat exchanger, and then returned the heated blood back in the vein, the femoral vein. And so it didn't have requirements for any kind of a pump or any other external kinds of things. So we had basically these are some amplifiers that amplify the signals. Then we have the PID controller in the display. Only 3 valves. And so here's our control algorithm where we have desired temperature. We measure the temperature. So the output, this is the thermocouple that's telling us what the actual temperature is, and then we're heating the blood to be able to reduce this error signal to 0. So we have the proportional, integral, and derivative. Now, when we design this, as is true for most PID controllers, you really don't know what the proportional, integral, and derivative controls constants are going to be. So in order to evaluate this and to come up with kind of a starting point here, what you have to do is you have to go down and do some kind of tests. So again, we connected it all up to LabVIEW, and we had in our lab setup we actually had to have a pump, and so this actually is the controller here. So this is the blood warmer here. This is what I just showed you. we measured, because we have a pump now, we have a pump that's pumping it, we had to measure the flow. And then we could perturb the temperature in this beaker, and we could measure kind of the response. And so that kind of gave us a first order idea of what the PI and D constants needed to be. So here's kind of a lab breadboard that tells us what that should be. Okay, and you kind of see where you have the desired, and then this might be the response that we actually got. So you can, in our little lab setup, you could add ice cubes and then see how quickly it responds. So basically, we have the temperature of our perturbation, and you can see how the controller follows that. It takes a little while for it to catch up. Okay, and so you can put ice in and take ice out. And so eventually we took this down to UTL Science Center at Houston, and we actually tested it and got data on 20 dogs and 20, we used 20 sheep. And so what we did here was we just bled the animal, induced hypothermia, and then tried to restore the temperature, with the controller. And that's kind of what the temperature curve looked like when we had the device working. Now, if we hadn't had the device working, this would have just kept going down. But you can see how it recovers the temperature pretty much to 37. Cardiac output, throughout this whole experiment is dropping, because every time you get this hypothermic, your heart quits pumping efficiently. And so you can see how the animal is getting closer and closer to death during the experiment. Just to follow up on the story, just to kind of, this is actually one of those successful, the student's name was Kevin Arun, and he started his own company down in Houston. And this thing worked good enough to where he became a government contractor. Now he's a multi-millionaire with his own company down in Houston. So one little project can launch you on a successful career. Point is that y'all are extremely smart, and so a lot of your ideas are really good, and a lot of them can actually make you a nice business. Any questions? That's all for today. We'll start from here next time.